So we'll get started. Hi, everyone. My name is Priya. I'm the Environmental Outreach Specialist at London Environmental Network, and I'm so excited to hear from Stephen Cornelius about residential air source heat pumps. I know I'll learn a lot from this event, and I hope you do as well. We'll be starting this session with a land acknowledgement. So thank you for coming out tonight. We want to start by acknowledging the history of the traditional territory and honor the long-standing relationship of the three local First Nations of the land and place in southwestern Ontario. The three long-standing Indigenous groups of this geographical region are the Anishinaabe, the Haudenosaunee, and the Napawak peoples. We would also like to recognize the three First Nations communities downriver, Dekshan-Zabi, Thames River, Antler River, which are the Chippewa of the Thames First Nation, Oneida Nations, and the Thames and Munising Delaware Nation. We strive to work with these communities to listen, learn, and restore natural area back to its original beauty, support environmental initiatives, and help our communities become climate resilient. So this webinar on your guide to heat pump for your home is one of many that we'll be offering, focusing on how you can make your home more climate friendly. We're working on a program called Greener Homes London to support Londoners in retrofitting their homes and making lifestyle changes to lower our carbon footprint. And right here, just looking at this chart, you can see that personal vehicles and housing are kind of the largest categories of emissions in London. So it's kind of empowering to know that you have the power to make those changes within those categories and have a big impact. And we're really close to starting up the program. So you're kind of getting a sneak peek into the community engagement side of the Greener Homes London program. So this will include one-on-one coaching to help you green your home. If you want to stay updated in the program, be sure to sign up. And I'll just put a link in the chat so you can sign up for a newsletter. And if you just go to the bottom of that link, you can sign up. So without further ado, I'd like to introduce our expert speaker, Stephen Cornelius. As an experienced business manager specializing in the air-to-air heat pump solutions from Mitsubishi Electric, Stephen has a passion for efficient, environmentally responsible HVAC solutions. He's currently managing the residential and light commercial business operations in Ontario, supporting a distribution network and working with all stakeholders as the industry recognizes to meet greenhouse gas reduction targets in Canada. So I'm going to stop sharing my screen and let Stephen share his.
Okay, let's the right one should be this one. Okay, hello everyone. I'm very privileged to be able to share this information with you this evening. I want to thank GEL for inviting me to speak with you today. So as mentioned before, my name is Stephen Cornelius. I'm the Business Development Manager for Ontario, specializing in our residential HVAC products for Mitsubishi Electric Canada. Not to be confused with Mitsubishi, the vehicle. We have nothing to do with them. My prime role is to liaise with distributors, property owners, government and non-government agencies to facilitate the adoption of heat pumps. So that's all I have to say about me. This will be the agenda, what I'm looking to discuss with you today. And we'll broach any other subjects that might be of concern to you. So why are we here today? Is it because you believe in climate change? Is it because we're the 5th highest CO2 emitters per capita? For some of you, maybe. But I assume it's because we all have some interest in living in better, more efficient spaces. My hope today is to convince you all that heat pumps are effective, efficient, and economical way to thermally condition your space. If you do any amount of research, and there's countless independent studies by government agencies and NGOs about the energy efficiency of heat pumps. So this really shouldn't be a question. The only real question is, does it make sense to use this technology in place of conventional systems? But because here in Canada, we are very natural resource rich, it makes a lot of sense that we've been dominated by fossil fuels to heat our homes. For the rest of the world, they're not as fortunate, and they've looked at alternative measures and have never looked back. There are two pervasive considerations that have plagued wider Canadian adoption: operating cost and operation at winter design temperature. So today I'm hoping to enlighten you to the fact that, unlike the fake news that the liberal media wants you to believe, cold climate systems do make sense. So a brief history about Mitsubishi Electric Canada. So in 1987, we opened our first division in Markham, which is where we currently have our head office. And we were the first company to introduce ductless technology to the market. And then in 1996, we introduced our P series, which was the first -40 product to provide low ambient cooling. This is more of a commercial product. And then in 2007, we introduced the Zuba-Central, which I'm sure many of you have heard of, and this is the beginning of the cold climate revolution. So what is the heat pump? Its name doesn't really convey what it does. So in the most simplest terms, it's an electric appliance that transfers heat from one space to another. And heat pump is the generic name that's given to the technology, which applies to a whole range of products in the market. So today I will address cold climate split systems, but there's also standard split systems, VRF systems, which are commercial, and they are centralized systems. And the key thing here is heat pumps are not electric heaters. So the basic thermodynamic premise that underlies heat pumps is that heat always goes to cold. And this is due to objects always wanting to be in thermal equilibrium. So this means that if there's something warm beside something cold, the cold object will absorb heat from the warm object, or the warmth will go towards the cold. For example, so if you're sitting in a space, office, or room, whatever, and you're sitting beside a cold window, that window is going to draw heat from your body, and eventually you will feel cold. So I'm going to let you know a little secret here. This is an industry secret that not many people know. Cold cannot be generated. Only heat can be generated. Now you're going to say, this guy doesn't know what he's talking about. I'm done with this. You know, what does he know? I have a refrigerator and it makes cold. I have a freezer and it makes things cold, right? It actually doesn't. What happens in your fridge and your freezer is that it absorbs the heat out of the space and it transfers that heat to the outside of the box. A system called the refrigeration cycle is how your refrigerator works, as well as your freezer and your AC, and of course heat pumps. So if you've ever been behind one of the older fridges, you'll notice the coils on the back, and they're hot. And that's because they're trying to dissipate the heat from the refrigerant. So as I mentioned, the heat pumps use a refrigeration cycle, except that it also works in reverse. It has something called a reversing valve. Of course, they couldn't come up with a more original name, which lets you change which space the heat is being absorbed from. So how does the heat pump produce heat in the winter, right? You're saying it's cold outside, but yet I'm getting heat inside. How does that work? So there's actual heat in the air until absolute zero, which is, absolute zero is on the Kelvin scale, but we would look at it as negative 275.15 Celsius. So once you get down to that level, everything stops moving, all molecular action stops, it's the end of the world. But above that, there is always some heat in the air. And using the refrigeration cycle, heat pumps are able to extract some of this heat energy, concentrate it, and then transfer it to the inside. So here we have a schematic of a heat pump system. So in the system, you have two heat exchangers. One we call an evaporator and one we call a condenser. But this is interchangeable because they both end up doing the same thing on either side. Compressor pressurizes the refrigerant from a low pressure vapor to a high pressure superheated vapor. It then passes through the condenser, which we say is the outside unit, and then it transfers that heat to the cooler air. And then when it becomes cooled liquid, then it goes through the expansion valve where pressure abruptly drops, causing flash evaporation, making it very cold, which then absorbs the heat from the air going across the evaporator. So as long as the refrigerant is colder than the air, it'll absorb heat from it. So a little history on heat pumps. They aren't new. They were created over 150 years ago. And as with all appliances, the technology has continued to advance. The majority of the world's population does not need cold climate systems. Canada being a small market in almost every industry. Our neighbors to the south, their majority in the warm climate, so therefore they're used mostly cooling. So cold climate systems are a very small portion of the world's market. You know, ourselves, the Northern European countries, obviously places like Russia. So getting the products here was something that Mitsubishi Canada had to work hard to develop systems specifically for Canada. And we have prided ourselves in being a leader in the market. And we consistently develop our technology so that we can reach lower and lower temperatures. So now, when we're talking about energy efficiency of heat pumps, we usually refer to something called the COP, which is the coefficient of performance. And so this is a ratio of the energy consumed by the unit compared to the energy delivered. So looking at a conventional system like an electric resistance heater, they have a COP of 1. So this is sort of the base. You have 1 kilowatt of electricity going in, and you can give out 1 kilowatt of heat energy. And so that's a COP of 1. Now, if you have a natural gas furnace, you may have seen numbers like 95, 96% efficient, which would be a COP of 0.95 or 96, right? So 100 being your 1. And again, we're talking about energy. So all the energy is not being provided as usable heat, but with a fossil fuel system, you basically could not get to 1. You can get it very close to 1, and that's where they strive to, but they could never surpass 1. And then when you're looking at oil and propane, they're even less efficient. So heat pumps produce numbers of up to a COP of 5, depending on the outdoor air temperature. And so how is this possible? Heat pumps don't use the electricity they consume to create heat. It simply runs the components, the fans, the compressors, the circuitry. Heat pumps, as I mentioned before, transfer heat from one space to the other. So then the warmer the outdoor air, the more heat energy there is to deliver. So in 2 slides, we'll see a COP chart for a cold climate system. But just looking at this slide here to try to help it make sense, I think you should be able to see the mouse. Okay, so we have your outdoor air, we pick up some heat, right, that runs through the coil, and then so now our refrigerant goes, hits the compressor, and then it's increases the pressure with increases the heat, and then now goes across the other coil, and then we brought air across that, and then it distributes heat into the space. And so here's the math again: 1 kilowatt of electric energy put in, and you got 4 kilowatts of heat absorbed from the outside, and it gives you 5 kilowatts of heat output. And so this would be a COP of 5 theoretically. Typically operating, you see COPs in around the 2s and 3s. If you're talking about a full heating season, 5 would be like plus 15, 16, 17, which really you're not using much heat in. So adoption in Canada for heat pumps has been relatively slow because we have an ingrained industry that likes doing what it's always done, and fossil fuel is cheap, and we're used to gas furnaces, so why change? But the heat pump industry has consistently gained year over year. So even with the pandemic raging last year, it was the largest uptake in the industry thus far. So currently there's over 800,000 homes with heat pumps in Canada and growing. And that number is very conservative. Driving this adoption is building science, improved air leakage rates, therefore reducing heating requirements for homes, and improved indoor air quality. Now, looking at efficiency, there's no better way to move through thermal energy than through a refrigerant. So the diagram here shows different conduits that you would move thermal energy through. So in most of our homes, we use air ducts. So that's represented by the large circle. And these are all proportional to each other. Some people may have hydronic heating, so radiators, right? And a boiler. So that's the 2.5-inch water pipe. So when you're moving that same quantity of thermal energy, you only need a 3/4 to 1/3 copper pipe to move refrigerant through. So when you look at space and even just materials, refrigerant is far more efficient. And so this diagram represents 3.5 tons of energy. And if you look at it from a homeowner's point of view, no more bulkheads if you were designed from new. So this here is a COP chart. And so the red line represents the efficiency of a 3-ton Zuba system, which is a centrally ducted system, and 3 ton is 36,000 BTUs. And it's being compared to conventional systems such as electric resistance heat, natural gas, and oil. So the electric line is the blue line, which is right at 1. And then we have natural gas being the yellow line, which is obviously below 1, and then oil below that. So if you look at the chart, even at winter design temperature, or sorry, below -30, you're still above a COP of 1. You're at 1.26, and then it just goes up from there. And so that is how much more energy efficient it is than your standard heating systems. Now, to be noted, as it gets colder, a heat pump system will lose efficiency. That's because it's harder and harder for it to pull that heat out of the air. But as long as the COP stays above 1, it's still more efficient than conventional system. And as a company, we're constantly striving to gain further cold weather performance. We guarantee 100% of the heating output at -15 for all our current systems, and 80% of the heating at -25. And our new products that are coming online, we have some wall-mounted units that are just launched this year, now give 100% at -20, and that'll follow through the rest of the line. But this is the target, to get 100% at -25, which would cover 98% of the population. Now, unlike conventional systems, which only cycle on and off, heat pump systems deliver temperate air consistently. So it's more of a constant flow of air than on-off. There's two-way communication between the thermostat, the indoor unit, and the outdoor unit. If you compare that to a conventional system, your thermostat only sends information to your furnace and say, turn on, turn off. There's no feedback going the other way. So a heat pump system detects changes in the room based on the set temperature, and then readjust the compressor speed to provide the appropriate level of heating or cooling as required. And this is what gives you a lot of your cost savings. So no hard startups, no running at max for a sustained period of times. And this is a huge improvement for occupancy comfort, because you get a constant feeling of warmth or cooling with a consistent flow of air. Now, the next slide is going to give you a better illustration of what I'm talking about here. So, we all like cars, and so the gray car represents a standard furnace, and the green car represents a heat pump system. And so you can imagine how much energy it takes for that gray car to get to the top of that hill, and then it has to, it goes straight down, but then now it's got to go straight back up, and it's going to keep going up and down like that. When it hits the set point, it shuts off, it goes down, and then when you're looking at the green car now, it just needs to get itself up into that zone where the set point is, and then it coasts from there on in. Now, operational costs. It ends up that we're a lot further along than we thought. As an industry, we really didn't have a strong idea of a direct comparison between, your gas furnace and a heat pump system. The concept was, and the thought was always that heat pumps are way more expensive to operate, and people only use them if they need them. Obviously, if they don't have natural gas or they're, off in the sticks or whatnot. But in 2020, we commissioned a study through Natural Resources Canada, and we said we really want to see an exact comparison, with the similar homes. What is the operating cost for a full heating season versus a heat pump versus a natural gas system? And it came out better than we could have expected. So if we look at the graph on the left, this is based on if you completely cut off your gas service and you have fixed energy charges, what we had over the pandemic. And you can see in every single jurisdiction in Canada, your heating bills would be less, so you'd be saving money over if you'd run a gas furnace. On the right side, it takes away the fixed charges that we had and go back to your time of use charges. So in places like Prince George or Winnipeg, it would be less efficient for them to have it, but every other region, you'd still be saving money. And then to take this a little bit further, this is a copy of my gas bill from December last year. And my usage charge was only $23.59, but I paid $60 in fees to, delivery fee, carbon charge, transportation, delivery to you. So you can imagine just that alone, if you were to cut off natural gas, you'd be saving that amount a month. So your electricity charge will go up by about 50 to 70 bucks, depending on the size of your home, but you'd be saving that money in fees. So you can see how really heat pumps aren't the expensive alternative. They're actually quite a smart alternative. And of course, if you had propane or electric or oil, you're way ahead. And now when we look at temperatures, so everybody says it's cold in Canada, and sometimes it is, and depending on where you live, it's colder. So I picked Ottawa because we do a lot of work in Ottawa. There's a lot of people in Ottawa that have heat pumps, and we tend to think of wind chill. That's what we hear on the weather report all the time. It feels like -25. It feels like -28. But we don't actually see those temperatures, and a heat pump system doesn't see those temperatures either. A heat pump system is only affected by dry bulb temperature, which is the actual temp. And so in reality, if you look at weather data going back years, we rarely get above -20 or below -20. So this is well within the operating range of a cold climate system. And even if it does drop below that, if there's some winter vortex that comes through, if it goes below, say it goes to -30, it might be there for a fraction of an hour. It's not sustained. It never sustains at those low temperatures. Now, up in Nunavut and Northwest Territories, yes, they do see those sort of temperatures. And they do have heat pump systems up there. They just have a backup for when it gets to those low temperatures. But down here, Ottawa's winter design temperature is -22. London, I believe, you're in -18, and Toronto, we're somewhere in between. So again, these are well within the operating ranges of cold climate heat systems. So now I'll run through some products and their applications. So these are some images of indoor units. They come in different shapes and sizes, depending what your needs are and what best suits the situation. The wall-mounted units are the most common product across any heat pump system. This is what you've probably seen in people's cottages, your grandfather's cottage. This was the standard. They're a bit of an eyesore, but they do their job really well. This is a one-way cassette. This unit, we'll see some images of it later, but this actually fits into your ceiling. It fits in between the joists, 16-on center joists, and then you just have this base plate that sits proud of the drywall. But aesthetically, this is very nice for a modern home. This one here is your ducted concealed or ceiling concealed. And so this is a small air handler. You can still duct from this, but it's got a very narrow profile where it's about 8 inches deep. And you can stick it over a closet or over a bathroom or something like that, create a small bulkhead for it. And then you can run 5-inch, 4-inch duct that can be run through the wall, that can be run, in the ceiling and whatnot. So this is really good for, if you want to zone a house and say have it upstairs. It's also good for apartments. But like I said, you can duct from these. Get over here in the floor mounted. This typically is seen to replace radiators. So if you had a hydronic system and you had rads, and then you were switching over to a heat pump system, this is sort of what would cover up that space. The 4-way cassette is a 2x2. So, if you were putting an addition on or something, then you could make space for this in the ceiling. But usually this is seen more in a retail or commercial application. And then the multiple position air handler, this would replace a typical furnace. You attach ductwork to it and it would run a central system just like we have in most of our homes. And then the outdoor units, again, come in various sizes depending on capacity. They could be a 1-to-1, which means one condenser to one indoor unit, or they could be a multi-split where the condenser serves multiple indoor units. And, they can be as small as 22 by 32 or as large as 52 by 42, but they've got a very narrow profile. The max width or depth is about 13 inches. So they sit really nicely beside a house. You can even attach it to the side of the house, but and these things are whisper quiet. We're talking about 50 dB, so they could be right under a window, which you definitely couldn't do with your AC system. Okay, so an image of a floor-mounted unit in a space. These come in from 9,000 BTU to 18,000 BTU. The slim duct unit, as I mentioned. One thing I didn't mention was that they come in low static and high static. So a low static, you wouldn't really put a duct in front of it because it doesn't have the power to push that air. So as you can see in this application, it would have a grill in front of it and it would distribute the air to that space. But with the high static one, that is where you could attach ductwork to it and it could serve a whole floor, no problem. This is an image of that one-way cassette in a space. And here's a cutaway of that one-way cassette. So you can see how it's set up in between the joists. Fine. No. Okay, and this is the multi-position air handler. You can see it ducted. So the return goes through the bottom and then goes out to the ducting throughout the house. And with a vertical air handler like this, you can attach an ERV, you can attach a dehumidifier. So again, just like your typical furnace, it would sit in the place down in your basement. And then just a quick look inside. You got your fan blower down at the bottom. This is your coil where the refrigerant runs through, which provides you your heating and cooling. Then you've got your circuitry up here. And again, your supply air comes out through the top. So here we're just looking at a vertical air handler in space. So, they can be used in apartment buildings, townhouses, detached homes. The air handling unit would take the place of any vertical air handler that is currently in place. And they provide conditioned air through your centrally ducted system. The difference is that you have heating and cooling in one system, and you have no venting requirements. And here we have the multi-split system. I'm not sure if many of you have heard of it, but these are ideal for any multi-level home. Because when you have a central system, it's conditioning for one set point, which wherever your thermostat is, that's what it's looking at. So when you go up to the bedrooms and say, it's got a high exposure to sun, the upstairs floor is going to be a lot hotter than the main floor. So then now, are you cooling for that floor? So you got to set the thermostat to cool for upstairs, but then the main floor is going to be a lot cooler. Now, when you have a multi-split system, you have zoning ability. So you can have multiple heads in the home, and you can have different zones where, this one's at 78, this one is at, 70 is way high. 72, you can have 68, you can have 74. They all have to be in the same heating or cooling mode, but they have their own set points. And so you can have up from 2 to 8 zones in a home, depending on the capacity of the system. And the next one will give you a better visual of what we do. Just quickly touching on this one here. This is a home in Toronto near High Park, and the homeowner split a Century home into 3 apartments. So they have 3 separate systems, but they're all multi-zones. So each apartment has individual zones inside that apartment. That's what this individual chose to do. But there's flexibility to do things different ways. But each apartment has multiple zones, and each apartment has their own system. And so here, looking at if you had a bungalow that was very open concept, you could basically have one wall hung head, and it probably could satisfy the whole space. But when you have a home with, maybe a room over the garage and, just very compartmentalized spaces, and depending on the orientation of your house and how the sun hits it, you might want to have different set points. And you may have a room that you don't go into in the summertime. So why are you cooling it, right? You just turn that system off. And then, the bedrooms maybe needs to be a little bit warmer, a bit cooler, but you can have individual control for the various zones in your home. So it is a smarter way to do HVAC. We're very conditioned to have a central system, but if you can do a multi-split or a zoned system, it is much more efficient and much better for your occupancy comfort. Now, the indoor units are relatively straightforward, and then the outdoor units are very versatile. So you can put them on roofs, you can put them on balconies, you can put them on a wall on the side of the house, you can put them near a window. If you put them on the ground, they have to be elevated so they're above the snow. And depending on the models, there could be enough pipe length to put them all in a common area if you're looking at multi-unit residential. Unlike fossil fuel systems, you don't have any venting challenges. You don't have to worry about, there's code obviously that dictates where you can put a vent and how far it can be from a window or a door. None of that is relevant. And of course, these systems are very quiet. If you look at any of the spec sheets, you'll see that you can barely tell they're running. If you're standing beside one, you have to look at the fan to see that it's running. And then you only need 6 inches behind the unit and 3 feet in front of it. So in homes that are very close together, again, you can put one of these on your wall and still not worry about the depth between you and your neighbor, because it only needs 3 feet in front of it. So here we have a heating performance chart, and this is showing the heating performance for 4 different size systems, the range of their heating, and their outputs at different temperature. And so on the right, specifically, it's a 2.5 ton model, and it shows you what your heating output is going to be at -25. So when we're designing for a home, or when an engineer is designing for a home, they're looking for what that output is going to be at the window design temperature, because that's what you're sizing the system for. Obviously, it'll have excess capacity as the temperature goes up, but you want to make sure that you can provide the heating for the home at window design temperature. And so this is a similar chart for a multi-split system. You have a larger capacity with the multi-split. They go up to 4 ton, whereas the one-to-one systems only go up to 3.5 ton. And as mentioned before, you could have up to 8 different zones with a multi-split. Now, for those of you that aren't brave enough to make the leap all the way to heat pump, there's an alternative, and we call it a hybrid setup. So currently, if you have central air, you have an evaporator or an A coil that's placed inside your furnace. And so your furnace moves the air across the cold coils, and that gives you your cooling. So now when you pair a hydronic coil with a heat pump, you can have your cake and eat it too. Use a standard heat pump, so not a cold climate, a standard heat pump, because you're not going to worry about the winter design temp anymore. You're going to use the hot water coil to cover that lower end. So your heat pump's going to run and cover your 3 seasons, and it's going to do it very efficiently. But then around -10 or -15, depending on the system, then the hydronic coil is going to kick in and cover off that heat load. Now, we do not make a hydronic coil, but we've partnered with coil makers, specifically direct coil, that can be packaged with our system. And then you can use either a full hot water tank, or you can use a tankless. I happen to have a builder up in Ottawa, a production builder, who this is their standard for their homes. So a standard heat pump system with a hydronic coil, and it's run off a hot water tank, I think a 60-gallon tank. Still looking for time. So let's look at a couple of projects. So this home here, this is in Campbellford, which is out east somewhere, and they had an oil furnace. They're not served by natural gas, and they were spending over $3,000 a year in heating. So they switched out to a cold climate heat pump. This is a 1,800 square foot bungalow. It was built in the early 70s, so it's very leaky. And they haven't looked back. They have been absolutely floored with this. And it happens that these people are in the industry as well. So, you know, what do I want to say? Being in industry, you know, they knew what the systems could do, and they had confidence in it. And so they put one in, and, you know, they were just floored about the fact that, you know, this system, even though it's less capacity than their old furnace was, is still covering the heat load of their house. And that's partly because a heat pump system, again, pushes out air consistently. So you don't have that time where the air can leak through and cool down the house. You're constantly pressurizing the house with that thermal energy, the heated air, or the conditioned air. And so it's much easier for that system to maintain the set point than it is for a fossil fuel system. And there's the unit inside and the condenser at the back of their home. This is Trinity Glen. This is in Newmarket. It's a co-op. They have 92 residential units there, and they were using electric baseboard heating. So they retrofitted with 2.5 and 3 ton systems. They happen to be multi-split systems. And so even with the added cooling, so now, you know, before obviously with electric heat, they just had heating. Now they have heating and cooling. They still have reduced energy bills. So this has been, and then on top of that, when you look at electric resistance heating, you don't have any airflow, right? It's all stagnant. The only way you're getting airflow is if you open your windows. So going from electric resistance to heat pumps, or even hydronic heat pumps, you're getting airflow now and filtration. So very huge upgrade. This is Bruce County Social Housing in Kincardine. They had electric furnaces. So electric coil in a furnace blowing air through a central system. And so these were replaced by 3 ton central systems. And they're seeing a 50% saving on their energy costs. And here are some images of, again, outdoor condensers. The one on the left is at a Airbnb I stayed at in Barrie. The one in the middle, this is a great golf home in Bradford. And then the one on the right is a Century home in downtown Toronto. And for those who are architect types that, you know, need everything to be aesthetically pleasing, you could possibly do this. This is a wrap. So essentially you take a picture of the side of a home, and then you create a wrap, and then you can wrap the unit. Now this is not standard by any means. This is extra and above, but these are just possibilities. And then looking at multi-unit residential, this is Skyline Development's Southfield Green project in Tecumseh. It's 140 units across 2 buildings. and they're using 1.5 ton vertical heat pump system. So this whole complex is going to be heat pumps. This is another Skyline development. This is Lancaster Park in Welland, and this is 86 units. And they are all various types of heat pumps. So we've got the SEZs, the PEDs, which are the slim ducted units. But again, this whole building is going to heat pump. And these are happen to be rental buildings, but the reason for going this way is the building owners can further isolate the cost for each unit. So this makes a lot of sense for them. And of course, lowering their carbon, they're trying to be environmentally friendly, lowering their carbon footprint and lowering emissions. This is another one for Skyline. They've done 3 buildings in the last 2 years, which is incredible. It seems out west, so I guess Guelph and westward, builders and homeowners are seeing that they can make a change and make a difference. Whereas in the GTA, it's very hard, it's very slow, and it's very resistant to change. So we're not seeing any large developments in the GTA by any means. Individual homeowners here and there, some nonprofit housing, like so TCHC is doing a lot of renovation and switching over to heat pumps, but nowhere near what people are doing out west, what I call it west. I don't know if I give details on this. So this is River's Edge. This is in Chatham. 55 units, 1.5 ton units, and 2 ton units. This one is Eve Park. This one is in London. This one hasn't been built yet, but it's looking to. Oh, they broke ground already, so they are starting this summer. 288 units. This is going to be a very advanced complex. They have electronic valet parking. They have solar panels all on the roof. They're taking it to the next level. But again, these are all heat pumps. And the last project I'll share with you is the most impressive net zero development in Canada. So this is the Citizen West 5 project, which is on 70 acres and fully sustainable mixed use development. Their vision was 100% energy efficiency. They were actually told they couldn't put any more solar panels on because they were generating too much electricity. They have their head office here. They have many multi-story buildings. Their head office is right here. These are retirement residences. They're going into phase 3 of their townhomes. Each phase was 75 units, and they're going into their 3rd phase. And again, everything here is heat pump VRF technology. Now, it's hard to stand behind your warranty when things are bunged up in the install. So if a system is not putting in correctly, there's going to be problems. Heat pump systems are very reliable. They're very consistent. We have systems that are going on 20, 25 years since we brought our systems here. But if they are put in by someone who is not experienced, if they're put together in a rush, an error is going to be made, and then there's going to be problems down the road. So we encourage everyone to contact a licensed and certified installer. If you contact one of our distributors, MITS-AIR, they can direct you to local contractors near you. But whatever system you use, whatever manufacturer, make sure that it's a licensed and trained installer, because that will guarantee you proper service of your system. We as a company, we train contractors. Whoever wants to get trained by us, we'll train them, because we'd rather them know what they're doing than just say, yeah, we've done this before, and go in and, make an error, and then, then there's just issues ongoing. And of course, that affects our name. We care very strongly about our reputation. We have a very strong reputation in the industry, so we want to make sure that everybody has a good experience. So if it goes in by a non-trained contractor, you only get 7 years warranty, whereas if it goes in by Mitsubishi certified contractor, you get a 10-year parts and compressor warranty. Now, hopefully I've left you all with a little more confidence in what a cold climate system can do. My wish is to leave a better place in this world for people like that person on the motorcycle there, which happens to be my daughter. And if we keep advancing with technology and build more efficiently and more environmentally conscious, then we're going to be doing things right by the next gen. And this concludes my presentation, and I think we can start our question period.
Okay, awesome. Thanks so much, Stephen. So we've had a lot of questions come into the chat during your presentation.
Right.
Yeah, so I hope you're ready. So the first one was, what would you suggest people do for days when temperature is under -20 Celsius?
Right. So again, our cold climate systems, they run down. So some of them run down to -25, and our Zuba systems run down to -30. And they'll actually cut out at 32 point something. So -20, not a problem. The systems will supply heat throughout that temperature.
Okay, awesome. And then we had a few people wondering if they could get a link to the Natural Resources Canada source data for operational costs.
Right. So the challenge there is that Natural Resources Canada hasn't published it yet, so we can't share it. Technically, I get in trouble for showing you that one page. This was the pandemic really has slowed this up because they should have published it by now. And I've been in contact with my contact there, and it's the federal government, so they're just going to get to it when they get to it. But unfortunately, until they publish it, and so what they'll do is, wipe our name off it and just make it a generic study, so that they're not representing us in any way, shape, or form. They're advocating for us. But once they publish it, then we can. But until that time, our hands are kind of tied legally.
All right, sounds good. So another personal question here. So 20 years ago, I worked in an office building that used heat pumps for HVAC, and there were always issues when the system switched from heating to cooling. Has this changed? Does it automatically switch between heating and cooling for the spring or fall when temperatures can fluctuate dramatically?
Right. So as you stated, that was 20 years ago. So a lot of things have changed. TVs used to weigh over 100 pounds. Now TVs, you can carry a 65-inch over your shoulder. So yes, technology has advanced exponentially from there. They automatically switch over, so there's no issues in that regard.
All right, awesome. And how noisy are the units?
Right. So, if you ever look at a spec sheet, you can see the actual DVs, but depending on the size, the smaller ones, I think, are as low as 40, but the big ones are generally around 50, 52. And so again, standing beside one operating outside, a lot of times you're looking at it to see if the fan's spinning. It is that quiet. Nowhere near what, like I have a conventional AC outside at my home, and it was moved from being under a window because it's way too loud. But that heat pump system, the vertical heat pump systems, are super quiet.
Okay, great. And we had a few kind of similar questions. So we talked a little bit about operational cost, but what about the installation and capital cost of a heat pump compared to a conventional unit?
Right. So installations cost, I can't speak directly to, as I'm not an installer and I don't install, but capital costs, yes, a heat pump system is more expensive than a furnace because it is two systems in one, right? So really, if you're looking at it, you would have to look at a high efficiency furnace as well as a high efficiency air conditioner, the cost of those two, and then compare that to a heat pump system. The heat pump system is still going to be slightly more. It's probably going to be, for a comparable size system, probably about $1,000 more. But you'll make that up over time, and obviously you have the interior comfort improvement, which many people can attest to that have systems in their home. But yes, it is more expensive. But right now, there's the federal Greener Homes program, which is offering up to $5,000 for a retrofit. So that significantly offsets the cost of making a switch if that was something you were looking to do.
Okay, and similar, also on the topic of retrofitting, we had a couple of people wondering about retrofitting a house with central HVAC already. Do you actually need to replace the gas furnace? air handling unit, or could you just swap out the AC unit outside with the heat pump, condenser, and controls?
Right. Yeah, so you have obviously two options. You could get a outdoor condenser with an A coil that would fit in your furnace and run that as a system. You're not getting the efficiencies of a heat pump because you're not going to get the variable flow from the fan. You're going to still have your on-off fan and your on-off thermostat. So you're getting some energy savings from the heat pump condenser in the way it does things. The condenser is going to be more efficient than an AC condenser, but you're not going to get the efficiency on the inside. So, but that's still an option. And then if you really want to see the savings, if you have an older furnace, say it's near the end of its life, then you'd switch that out, throw in a vertical air handler with an outdoor condenser, and then go from there.
Awesome. And then we had someone wondering why we don't see the exterior unit on the multi-res buildings.
From like the slides that I showed?
Yes.
Well, first of all, those were renderings of the buildings. They weren't actual shots of them. But it depends on where they locate the condensers. So the condensers can be on the balcony. So because they're only going to be a ton and a half, two. They're going to be the smaller units. So I didn't put in one. There was one I had of Vilnius Manor, which is downtown Toronto. It's a retirement residence. It's 22 stories. And so they tucked them up in the corner on the balcony. So it's up and high and it's sitting on the wall. And that's where they've sat for the past 10 years. But typically with a multi-res building, they'll try to put them all in one spot. So they'll put them all up on the roof and then run lines down to the individual suites. But it all depends on what they're thinking and aesthetics and whatnot. But there's options because you can get line runs up to 250 feet, depending on the system. So that would make it easier for you to have all of them set up on the roof and then run the lines to the units. But if it's a 20-story building, you're not going to have enough line length to make it down to the first floor. So therefore, you'd have to have a secondary area where you have your condensers. But there's options. But there are buildings that put them on the balcony, and there's no problem.
Awesome. And in your opinion, what would you say are kind of the most common reasons for people to refuse getting a heat pump, and what are the biggest motivators for people to get a heat pump?
Well, the biggest resistance to heat pump is worried about it being able to heat their home in the winter. That's always been the biggest thing. And in the past it was valid because 20 years ago they couldn't go very low. They were down to -5, maybe -10, so that wasn't going to cover it. But nowadays they can operate that low. They are viable, but it's education. So I myself, I speak to municipalities, I speak to property owners, whoever, to get them to understand that technology has advanced since the last time they saw one, which might have been at their grandfather's cottage or whatever. And then operating cost was another big thing. It's going to run my electricity bill way up, but it ends up not being true because it's not using electricity to create your heat like an electric resistance heater, right? It's just using electricity to run the system. So those are the two biggest things: winter operating and cost. But then once we've alleviated those concerns, then now people get past that, and also referrals, real life experiences, knowing someone who has one, or getting to experience a place where that's what's running the HVAC system, and people get to see like, oh wow, this really does work. It's like I said, there's countless studies that are available on the internet that will tell you about heat pump systems and how they work and how efficient they are. So the biggest resistance we have found is actually through the trades industry, where again, they've always done gas and oil or propane or whatever, and they don't want to switch. It's easy, it works for them. Why would they want to switch into something new? So it's really homeowners and property owners that are driving the change, saying, I want something better, I want something more efficient, I want better occupancy comfort. But the industry itself, like many industries, doesn't like changing. So therefore, they're holding back a lot of the adoption. But if you go anywhere else in the world, Australia, Europe, Asia, they have heat pumps everywhere. Like heat pumps last year in Germany surpassed boilers, which were their #1 heating system. So, the rest of the world sees the advantage and they're moving that way. But again, they have less natural or fossil fuels.
Okay, awesome. And when it comes to really old heritage homes that maybe run on propane, is the installation harder?
No. So if you have a central system, the installation is not harder because you're removing the existing furnace and replacing it with the air handler, the heat pump air handler. So that part is relatively straightforward. Just reconnecting the ductwork. There might be a size difference, so they have to make some adoption there. But that's basically it. And then you run the lines out to the condenser outside. But one of the images I showed was a century home in Toronto that was built in, at least the early start of the 19th century. And I happen to know the owner just from speaking to her. She switched out a gas furnace for a heat pump system. She's been running it for over a year now, tracking her bills, and she's ecstatic with it. It's worked out fine. And we're talking about a home that's quite leaky. Like she really hasn't done much for the insulation, so still a leaky old home, but she's enjoying her system, so it's working well. And those are the living examples are really what count, right? We can put anything we want on paper, but it's the real life examples of homes that have systems in them that aren't buttoned airtight, that leak a lot, and have a system that works well for the occupants. That's the best evidence we could get.
Awesome. And I just see a few comments on the Greener Homes grant, and I know you touched on this a little bit, but I'm just going to reply and say you can use the Greener Homes grant to get a heat pump. And yes, you do need to get an EnerGuide audit before you get access to the Greener Homes grant. The grant is up to $5,000, but then you can get up to $600 to cover the EnerGuide audits as well. But if you want help trying to figure that out for your house, that is something that we might be able to help you with through the Greener Homes London. So just again, I'm going to link that in the chat so you can sign up to stay updated on that and figure out how you can get support from us in the future to sort out figuring out how to get access to the grants. Unless anyone has any super last minute questions, I'm going to do our closing remarks here. So thank you again, Stephen, for this presentation. It was so informative. And we're gonna wrap up. I'm going to shout out our newsletter and ask you all to follow us on social media. Thank you all for your participation and amazing questions during the event. And last thanks goes to all of our sponsors. We also have a short feedback surveys that hopefully you all can make the time to fill out. I'm just going to link it quickly in the chat here, and I'll also send it out in the email after the event. I'm also going to make sure that you all have a link to the replay of this event in case you want to go and watch it again. And that is the end. Thank you all for attending.
Bye, everyone. Thank you for having me.
Bye.